Okay, students, now comes another question, workout part, just to apply principle of mathematical induction to show that this is true for any whole numbers. So let's now do that together. So simple. So let me show you how it's done. So what you need to do is you have to say first this as p of n. The variable used here is n, so you may call this saying as p of n. So we're going to verify that this 6 to the power of n minus 1 is divisible by 5 for whole numbers. True, actually it is true, it works. So the question is, how can you show this using principle of mathematical induction? So as you know, there are certain steps we need to pass through. So the first step is checking for the first initial number, and we know that the set of all numbers starts from 0, so put 0 there. So when you put 0 there, it will be 6 to the power of 0 minus 1. And we know that 6 to the power of 0 minus 1 is 0. And 0 is divisible by 5 because 0 divided by 5 makes 0. So it's true. So if this is true, we need to proceed. Now comes step 2. We have to assume that this is true for a certain natural number k. So if we assume that it is true for a certain natural number k, we are accepting that this p of k is true. If p of k is true, the saying of 6 to the power of k minus 1 divisible by 5 is true, so we accept this. And if we accept this, 6 to the power of k minus 1 equals 5 to the power of n for some n an element of natural number, because we said that this 6 to the power of k minus 1 is divisible by 5. If it's divisible by 5, it's going to be a multiple of 5. That's why I wrote it as a multiple of 5. But this is actually the same as this one. You can directly shift this minus 1 to the right, and you can have 1 plus 5n. And now we accept this as a true saying, and having this into account, let's now show that the statement is true for n is equal to k plus 1. That is to say, show that this is true for p of k plus 1. But we knew that p of k plus 1 is this one. It's a matter of putting k plus 1 here in n. 6 to the power of k plus 1 minus 1 is divisible by 5. So our intention is to show that this is true. So we have to now create a mechanism where we can use the step 2, that is this saying. So we need to create a means of writing this 6 to the power of k plus 1 minus 1 like this form. To do that, very simple, it can be done like this. 6 to the power of k plus 1 minus 1 is the same as 6 times 6 to the power of k minus 1. I can write, but I knew that this 6 to the power of k is already 1 plus 5n because it's accepted in step 2. So in place of this 6 to the power of k, you can have 1 plus 5n minus 1. So if you just carry out or simplify this, you will obtain this to be 5n plus 5. So you can now take 5 as a common out. So I finally obtained this being a multiple of 5, 6 to the power of k plus 1 minus 1 being a multiple of 5. So what I proposed first for k plus 1 now comes being true. So finally, by the principle of mathematical induction, the entire statement is true. So it's a matter of applying these 3 steps, students. So just apply them one by one and try to show. So the statement is true for any n whole numbers. Now comes question number 26. It is about graphs of rational function. So you are given a function f of x equals 2 minus x over x squared minus 4. So how can we find the domain? Clearly, the domain of the function is the set of all real numbers that can make, our function defined. So what we need to do is we have to observe the denominator. So try to make our function free from these values that can make our denominator 0. So the denominator gets 0 if x is either positive 2 or minus 2. So the domain is a set of all real number minus 2 to 2, minus 2 and 2. This is just to say that you are free to use any number in x for f to have meaning. But when you take minus 2 and 2, everything goes wrong or everything goes undefined. So the domain is a set of all real number except minus 2 and 2. So what follows says to find the intercepts of the graph of f. So in order to find the intercepts, first let's simplify. Students, this is x squared minus 4, so we can write this as x minus 2x plus 2. And this is 2 minus x, so I can write this as minus of x minus 2. So I now do have a tendency to cancel these two, so I do have minus 1 over x plus 2. So from this, as you see, I'm not having x-intercept, because if I make y 0, no value can make this 1 over x plus 2 0. So because of this, I'm not having x-intercept. And what about the y-intercept? When you substitute 0 correctly in x, I can obtain negative 1 over 2. So negative 0.5 is my y-intercept, okay? So the graph crosses the y-axis at minus 0.5, but it doesn't cross, or it doesn't touch the x-axis, as it has been, you see, clearly stated here. Now when you come to the vertical asymptote, students, the vertical asymptote is the values that can make your denominator 0, but now the numerator 1 in some case. So this is minus 2. You see, when you put minus 2 here, it will be meaningless. So x equals minus 2 is the vertical asymptote. And here, the other approach is, as you are approaching to minus 2 from the right side, y goes to minus infinity. Because as you are using minus 2 from the right side, you are using minus 1.9, something like that. Minus 1.9 plus 2 makes positive, and negative divided by positive makes negative. So negative infinity comes. The same analysis can also be done as you are approaching to minus 2 from the left. So as you are approaching to minus 2 from the left, you may use minus 2.0, something like that. Minus 2.0, something like that, plus 2 makes negative, 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 positive, so you do have positive infinity. So in both cases, you do have either positive or negative infinity. If this happens, this line, x equals minus 2, the vertical line is the vertical asymptote, students. What about the horizontal asymptotes? What happens as x is far away from the positive, from the y-axis, the vertical line? As x is going away from that, you see your function f of x is closer to the x-axis, because as x goes to infinity, 1 divided by a large number gets closer to 0. So y equals 0 is the horizontal asymptote, because as x goes to infinity and as x goes to minus infinity, y goes or approaches to, you see, 0. Y approaches to 0. So our asymptotes are, you see, x equals minus 2, vertical asymptote, and y equals 0, or the x-axis horizontal asymptote. So our graph gets closer to these two lines, okay? So proceeding to the other part, you see, students, there is a value that can make both 0 here, and this value is number 2. If you observe here, to make this 0, again, to make this 0. So if you substitute 2 here, 1 over 2 plus 2, 1 over 4, so x2, negative 1 over 4, which is negative 0.25, right? x2, y negative 0.25. This is a place where a hole is going to exist at, because even if this function is defined at 2 and negative 0.25, this is not defined at 2. Okay, hence, in order to show the graph of this one, we must have a hole for the graph of this. Sketching the graph of this is the same as sketching the graph of this one. The difference is, here we must put a hole at 2, negative 0.25 for these plots, okay? And then it's going to be this one, okay? Because this one is not defined at x2, y negative 0.25. So the graph looks like this, as you see. You see, students, I'm having here a hole at x2, you see, at x2, y negative 0.25, we are having a hole. So this is a graph of our function. So proceeding to the next one, we are having question number 27. It says, find all the cube roots of z equals negative 1 plus y. So we have studied how we can find, you see, nth root for complex number. So the first thing is to find the modulus. The modulus of this complex number is the square root of the sum of the square of the real and the imaginary one, minus 1 square plus 1 square makes radical 2. And then we have to determine the argument of that. And the argument of that is tan inverse of y over x, which actually is 1 over negative 1, because the real part, the imaginary part is 1, the real part is minus 1. So 1 divided by minus 1 is minus 1. So tan inverse of minus 1 is 3 pi over 4, and this is an angle line between minus pi and pi, so it will be considered as capital A argument of this complex number. Now, for n equals 3, students, I'm taking n3 here because you are asked to find cube roots, and here k needs to be from 0 to 2, 0, 1, 2, because so it has to be up to n minus 1, or n is 3, 3 minus 1 makes 2. So using the derived expression in our classroom, zk equals the third root of r. Actually, it was the nth root of r because n is 3 now. Directly put 3 there. Cosine of theta plus 2k pi over 3. I sine theta plus 2k pi over 3, because here 3 is used because it was actually n, but now n is 3. So we can have this k 0, 1, 2. So for each of these k values, we are going to determine now this zk. So from the first one, zk is going to be this. Look, r is what, students? R is radical 2. So the cube root of radical 2 is to the power of 1 over 2 times 1 over 3, which actually is to the power of 1 over 6, right? 6 root of 2. So when k is, students, 0, you do have 3 pi. You are going to have this, students, where you are going to have this. And when k is now, this is generally for any k value. Now let's substitute these values. When k is 0, this can come, students. When k is 0, you can obtain this as 1 root. When k is 1, you'll obtain this as a second one. When k is 2, you'll finally obtain this one. Okay? So all these 3 cube roots are now obtained in such a way. This is going to be the last one for, you see, this final examination paper. I hope it will help you very much, students. It says find the center, vertex, focal points, co-vertexes, and eccentricity of the ellipse given here. And finally, you are also asked to find the sketch. So the solution goes like this. As you see, the ellipse looks like this one. So move 33 to the right, you do have minus 33, collect like terms together. As I explained earlier, you do have this one, x squared plus 2x, half of 2 is 1, so square 1. And then 4 can be taken as a common out, then y squared minus 6y, but half of minus 6 is minus 3, square 9 can come, so minus 33 is here, so 1 directly taken, but 4 times 9 is 36 taken, so this makes this one. So divide both sides by 4 to have a standard form of this ellipse. So you are having now this expression. So clearly x is squared, so the horizontal axis is our major axis. So the center is a value that makes this to 0, minus 1 and 3. So our a is 2 square root of 4, b is 1. So c can be obtained by using the relationship between a, b, c. C is a squared minus b squared, a and b are known, 2 squared minus 1 squared equals 3. So the vertices are h minus ak and h plus ak, because it is located to the right and to the left. So you need to move a unit to the right and a unit to the left. So when you do so, h and ha and k are known. So it's a matter of now plugging all this. You'll obtain minus 3, 3 and 1, 3. The focal points are a matter of adding c to the right and to the left. Subtracting and adding c on h, because our, you see, major axis is horizontal, so it will be like this, as you see. And the co-vertices are basically, you see, b unit up and down. So you operate this on k, because your center is hk, so you are going to move b unit up and b unit down. So hk plus b, hk minus b, so hk, b already, all everything are known. Substitute, you will obtain these values, as you see. So this centricity value you see over a, so we knew what c is, it's already obtained, it's radical 3, and a is 2, so radical 3 over 2 can come. So clearly, as you see, students, what you need to know is you have to know the type of the ellipse first. Once you know that, you see, the center is hk, so if the ellipse is having a major axis horizontal, so the vertex can be obtained by simply operating on h plus a, h minus a, taking k as it is. And the focal points can also be obtained by adding c and subtracting c on h, because if it is horizontal, you just operate on the horizontal line. The co-vertexes on the k, the y component on the k, in such a way you can simply identify. And the sketch looks like this, as you see. Look, the center is at minus 1, 2. Look, here it is. The center is at minus 1, 3. Here we have the vertices a and a prime, and the co-vertices are also labeled here. So x1 and y3, here x minus 3 and y3, everything is labeled here. So in such a way you can determine, you can sketch the graph. I hope everything is simple. Thank you.